Good afternoon, everybody. Today we are going to discuss a new topic, balancing of rotating bodies. So for that, first you have to understand what a rotating body is. Rotating body examples from industrial applications of point of view would be considered as turbines, pumps, motors, even a ceiling fan, or the wheels of any automobile vehicles. That can also be considered as rotating bodies. There is a distinctive difference between rotation and revolution, so that we should also keep in mind. Many of you perhaps know this difference, but let me reiterate this again. Rotation means the rotation will be about the body axis, but revolution means about an axis which is outside the body somewhere else. For example, Earth revolves round the sun. It is not rotating, but it is revolving round the sun. So it is revolution. But either of these cases, we can apply the concept of balancing very easily and effectively. So at the beginning of this, we first try to understand what are the possible causes of unbalance usually occur in these rotating bodies, that means turbines, pumps, motors, etc. So possible causes means, suppose for that we have taken one example of a shaft carrying a symmetrical circular disc, and this one a shaft carrying an unsymmetrical object. So for the first case, this disc is mounted on the shaft during the assembly operation, and after assembly it may be found that the center of gravity of this disc may lie outside the rotating axis. That means the central gravity of this system, shaft and this system, would lie away from the axis of rotation. So if this happens, there will be distance between the axis of rotation and the central gravity of the disc. Say that distance is r. So when it is rotating with some angular velocity omega, this central gravity mass would experience a centrifugal force m omega square r, radially outward direction. And this force will exist only when the system is rotating. When it is stationary, of course, this value will be 0 and there will be no unbalanced force. So this m omega square r appears due to this assembly line error and the mismatch of the central gravity and the axis of rotation. But on this case, if we have an unsymmetrical object on the shaft, the unsymmetrical object would definitely have central gravity away from the axis of rotation. So by design itself, the central gravity would lie away from the axis of rotation, and of course here it would also experience the centrifugal force m omega square r. So what we observe in these two cases, that either by the assembly error or by design itself, the central gravity lies away from the axis of rotation, and that would develop the unbalanced force, that is m omega square r, in these rotating bodies. So this is the root cause of unbalanced forces. Hope you understand this. Now once we understand this feature, next part is how we develop some technique to solve these unbalanced systems. So we want to make this system balanced. So for that, what we propose that if we attach any mass, suppose mb, at some radial distance, say rb, then this added mass would also have the same angular velocity omega. So it is also rotating with this as an integral part. But since we place this mass mb at diametrically opposite to this mass m, so it will experience a centrifugal force which is radially opposite to the unbalanced force. So this would balance this unbalanced centrifugal force, and here we can then write mb omega square rb equal to m omega square r. So omega square get cancelled, so it is simplified as mb rb equal to mr. So by putting an balanced mass exactly diametrically opposite to the unbalanced force, we can easily balance this system. The same principle can also be adopted here. So whether it is symmetrical or unsymmetrical, it doesn't matter. If we have one unbalanced force, the plane of rotation, we can put one balanced mass at the diametrically opposite location and balance it. So this is our expression. Now before we proceed further, we would like to show some way of representation of this in two-dimensional diagram. Because every time if we draw this isometric or perspective views, it is really very difficult, particularly for complex geometries. So for that, what we propose that we represent this in two-dimensional form. So for that, suppose if we look from this side, from the front side, then we can draw this like this line representation, and we could show only the unbalanced part like this. So this portion represents the radial distance from the axis of rotation of the shaft, and this product MR represents the proportional force. So instead of writing the centrifugal force every time, we are writing here the proportional force. So proportional force means mass multiplied by radial distance. So unit will be kg meter. And if we look from the right and draw it on the left hand side, we can show the side view of this, and we can show the location of the mass. So suppose this is our reference axis, horizontal axis, and we put our mass here. So on the side view we have this, say MR, and this makes an angle of theta with respect to the horizontal reference line. So with respect to this horizontal reference, this location of this MR is at an angle of theta in the counterclockwise sense. So from the side view we can show it this angular position. So front view gives us the position of the mass and R here, and side view gives the angular position. So this is one way of representation of this unbalanced masses of rotating bodies. So it is called, you can say, representation. Now, if you want to put here this balance mass at the diametrically opposite location, say it is MBRB. So of course, mathematically then MR equal to MBRB, what we have already derived here. Okay. So if we follow this, then it could be perfectly balanced. Now suppose there could be a real situation where we would observe that we cannot place the balance mass exactly at the diametrically opposite location due to inaccessibility of the position. Okay, so if this diametrically opposite location is not available to us, then we cannot add here any mass, of course. So in that case, we propose a different approach. Instead of taking one mass here, what we propose here to put two different balance masses. Say one balance mass here, MB1, RB1, and another balance mass here, MB2, RB2. And in that case, of course, this unbalanced force must be equal to sum total of these two balanced forces. So one equation could be MR equal to MB1 RB1 plus MB2 RB2. Since omega square get cancelled from this expression, so we are not writing that omega square every time. We are expressing with the help of proportional forces only. But since we put the balance masses onto different planes, they could constitute a couple. So moment will be there. So suppose with respect to one end, the distance of this force is A, distance of this force is B1, distance of this force is B2. Then we can take moment about any point, this end. So MR into A equal to MB1 RB1 into B1 plus MB2 RB2 into B2. So solving these two equations, we can find the unknown terms. Now these two equations would be now essential for balancing this system, because we could not find any available space exactly diametrically opposite location of the unbalanced force. So that's why we have to put two balance masses at two different planes, and it gives rise to two different equations, force equations, moment equations. Okay, so hope you understand this now. Now let us now try to classify these different types of balancing. So we start with this case 1. What we observe that we have only one unbalanced force, say M R, and we balance it by putting balance mass M B R B. So this is one case. Case 2, what we observe here, the unbalanced force is there, but due to inaccessibility of space in the diametrically opposite location, we put two balance masses at two different planes, say MB2, RB2. Now we would like to observe these two things. Here what we find that due to the application of this force and this force, both are diametrically opposite directions, so these two forces balance each other perfectly. So there will be no stress develop in this shaft due to the presence of this. But here what we observe that this force is acting here and these two forces are acting on two different planes. So obviously what we observe here that this shaft will be subjected to bending moment. So there will be some induction of bending stresses in it. So in these two cases, first difference is this is perfectly balanced. So externally it is balanced. At the same time, internally also there is no stress level. So internally also it is balanced. But here it is externally balanced, okay, fine, dynamically balanced. But internally it is unbalanced because of the presence of bending stresses again. In these two figures, another common feature is when we place this balance mass diametrically opposite to this, by putting this, what we did actually, the resultant center of gravity of this whole system now lie on the axis of rotation here. So center of gravity of this system, whole system, after putting this balance mass, is now on the axis of rotation. So here also it happens the same thing. That is the resultant center of gravity would lie on the axis of rotation somewhere, but the difference is it is externally balanced, but it is externally balanced but internally unbalanced. Another case we can examine. Suppose this is a shaft and the center of gravity of the mounting etc. lie somewhere here, say it is little away from here. Okay, so there is some distance, and we know when it is here, the gravitational pull will pass through this axis of rotation. But if we twist it slightly and it is placed here, then the gravitational pull would act through this way, and this would, of course, a moment will be developed then about the axis of rotation. And even though we are not rotating this shaft, still it will automatically twist it down. It will roll or rotate on its own till the central gravity location comes here and the axis passes through the central gravity, coincides with the axis of rotation. Again, if we place it somewhere here, it will rotate in the opposite direction till it attains the same things. So what we observe here, that in static condition, if we slightly twist it and if it stays there, then we can say that it is statically balanced. But if we find that after twisting slightly, it does not stay here, rather it automatically rotates either this way or that way, then we call it statically unbalanced. Okay, so to make the system statically balanced, what we can do is the central gravity of the resultant system must lie on the axis of rotation. If it lies on the axis of rotation, then it will be statically balanced. Now let us consider this case again. This is one force this unknown force, unbalanced force, and here we have say force F1 and here we have say force F2, the balance forces. By putting these two in such a way that this force equal to sum of these two forces, so its resultant central gravity could lie on the axis of rotation. Fine. So it will be statically balanced. But if we do not add this, and if these two are equal, then also we can find that it is statically balanced because the central gravity lies on this point. But when it is rotating, these two forces appear and they would constitute a couple because these two are equal in magnitude, opposite in directions, only separated by a finite distance. So even though this magnitude and this magnitude are equal and their central gravity lie on this axis of rotation, but still when it is rotating, it constitutes a couple. So a couple will be developed during rotation. So in dynamic condition, again it will be unbalanced because of the presence of unbalanced couple. In static condition, the central gravity lies on the axis of rotation, so it is perfectly balanced. But in dynamic condition, it is unbalanced. So once it is unbalanced, so its couple would be acting like this. So it should be balanced by another couple in the clockwise sense at the support reactions. So this couple can be transferred to the support reactions, and the supports will sense the presence of some additional load due to the presence of unbalanced couple. Okay, so that's why this couple must also be balanced. So only force balance in this case will not be sufficient because of the dynamic unbalance present here. So we have to form the coupled equations so that it could be dynamically balanced. So in summary, what we observe here, that for static balancing, the necessary condition is the central gravity must lie on the axis of rotation, and to make this, only the force balance equation is sufficient. But for dynamic balancing, we have to form additional equation, that means coupled equation, or sometimes we call moment equation also. So force equation and the coupled equation both are essential for the dynamic balancing. Okay. Thank you very much.